If we want to send people to Mars or even deeper into space, what kind of engine will we use? Sci-fi has given us ideas like warp drive and hyperdrive. But right now, those are just fiction. What we do have is nuclear power. I know, a nuclear spaceship sounds a bit crazy, but it's actually our best bet for long-duration space flight. First, let's quickly cover today's rocket engines. Most rockets use liquid fuel. You mix a fuel like refined kerosene, called RP1, with liquid oxygen, ignite it, and the explosion creates thrust. SpaceX's Falcon 9 uses this. It's cheap and stable, but it leaves a carbon residue called coking, which makes reusing engines harder. The next generation, like SpaceX's Raptor engine, will use liquid methane. It's abundant, cheap, and about 20% more efficient than kerosene. This means we can go faster, farther, or carry less fuel. Since methane is also on Mars, we could theoretically produce fuel there for return trips or journeys deeper into the solar system. So, where do nuclear engines fit in? It's important to know we're only talking about using them in space, not for launching off Earth. Methane engines are perfect for overcoming gravity. Once in orbit, a nuclear engine would take over. There are two main types. The first is a nuclear thermal rocket. It uses the heat from a nuclear fission reaction, the splitting of uranium atoms, to superheat a propellant like liquid hydrogen. The hydrogen rapidly expands into a gas, which is then shot out of a nozzle to create thrust. No combustion means no need for heavy liquid oxygen, freeing up space for more fuel or cargo. This makes the engine incredibly efficient, but it has a lower thrust-to-weight ratio, which is why it's not great for launch. The second type is a nuclear electric engine, or ion thruster. Here, the reactor's heat is converted into electricity, which powers an ion drive. This engine uses electricity to charge a gas like xenon, pushing the ions out to create a very gentle but continuous thrust. NASA already uses solar-powered versions for deep space probes. They are super efficient and can run for years, but they are very slow to accelerate and decelerate. The real game changer is combining these systems. Imagine a ship that uses a powerful nuclear thermal engine for the main burns and an efficient nuclear electric engine for long-term cruising. With this technology, a trip to Mars could be cut from 8 months down to just 100 days. This is huge. The launch window to Mars only opens every 26 months, so faster trips mean more can be done. Plus, it minimizes the crew's exposure to the harsh radiation of deep space. This isn't a new idea. NASA's Project Nerva was developing nuclear thermal engines in the 60s and 70s for a Mars mission before it was cancelled. Today, the concept is being revived. The US Congress has approved funding, and Russia's space agency, Roscosmos, is allegedly working on a nuclear-powered space tug called Zeus, designed to travel as far as Jupiter. But is it safe? Actually, yes. The reactors would only be activated once the spacecraft is safely in orbit, far from Earth. If a launch failed, the reactor wouldn't be active and is designed to remain contained, preventing radioactive material from scattering. In space, the biggest radiation threat to the crew is still the sun and the galaxy, not the reactor on board. Nuclear power isn't just about getting to Mars faster. It's the key to establishing long-term bases on the Moon or Mars, where solar power is weaker. It could power entire space stations, transforming them from cramped labs into sprawling research facilities. It even makes settlements on the moons of Jupiter a distant, but real, possibility. Mars is just the beginning. Nuclear power could unlock the entire solar system. What do you think? Where could nuclear rockets take humanity? Let me know your thoughts in the comments. Thanks for watching. If you enjoyed this, hit that like button and subscribe for more deep dives into the new space race. We'll see you in the next one.